Welcome, fellow cosmic wanderers, to this gentle journey through the heart of our solar system. Whether you're settling in for the evening or finding a quiet moment in your day, I'm delighted you've chosen to explore with me the most magnificent star in our corner of the universe, our Sun. If you're new to this channel, know that you found a place where curiosity meets calm, where the vastness of space becomes a source of wonder rather than overwhelm. I'd love to hear from you in the comments. Where are you listening from tonight? Are you watching the sunset from your window? Or perhaps it's already dark where you are. There's something beautifully fitting about discussing our Sun while experiencing the rhythm of day and night that it creates for us. If these gentle explorations of the cosmos bring you peace, I invite you to subscribe. The universe holds countless stories, and we have all the time we need to discover them together. These amazing visuals are here for you, but there is absolutely no problem if you doze off midway through the video. Feel free to close your eyes, breathe deep, and let me take care of the rest. Now, let me paint you a picture that might surprise you. Imagine holding a grain of sand between your fingers. Such a tiny, seemingly insignificant speck. Yet, if our Sun were the size of that grain of sand, the nearest star to us would be sitting 4 miles away. 4 miles of emptiness, with just 2 grains of sand representing the closest stellar neighbors in our galaxy. This gives you a sense of just how alone we are with our Sun, how intimate this relationship truly is. But here's what's remarkable about our particular grain of sand. It's not just any star. It's the star that makes everything possible. Every breath you take, every drop of water you drink, every plant that grows, every weather pattern that shapes our world. All of it traces back to the nuclear furnace burning 93 million miles above your head. Our Sun isn't just a light in the sky. It's the conductor of an orchestra that includes every living thing on Earth. For thousands of years, humans have gazed upward and wondered about this blazing disk that brings us light and warmth. Ancient civilizations built monuments to track its movement, created gods in its image, and organized their entire lives around its daily journey across the sky. They understood, perhaps more intuitively than we do today, that the Sun wasn't just important. It was everything. The ancient Egyptians called it Ra, the king of the gods. The Greeks knew it as Helios, riding his chariot across the heavens. The Aztecs worshipped Tonatiuh, the sun god who demanded sacrifice to continue his journey. These weren't primitive superstitions. They were profound recognitions of a fundamental truth that modern science has only recently begun to fully appreciate. Our Sun is not just a star. It's the architect of our entire world. But what exactly do we know about this cosmic furnace that governs our existence? What secrets have we uncovered about the star that makes life possible? The answers are more extraordinary than any ancient myth ever imagined. Our Sun is what astronomers classify as a G-type main sequence star, a yellow dwarf, though calling it a dwarf is somewhat misleading when you consider that it contains 99.86% of all the mass in our solar system. Jupiter, that giant among planets, represents most of the remaining mass, while Earth and everything on it, including every human who has ever lived, accounts for barely a rounding error in the cosmic accounting. To truly grasp the Sun's scale, consider this. You could fit about 1.3 million Earths inside our Sun. If Earth were a marble, the Sun would be a sphere about 8 feet across. The surface area of the Sun is nearly 12,000 times greater than Earth's. These numbers start to feel abstract, but they point to something profound. We live in the gravitational embrace of a giant, a star so massive that its influence shapes the orbits of planets billions of miles away. The Sun's core, where the magic happens, reaches temperatures of about 15 million degrees Celsius. At these temperatures, Hydrogen atoms move so fast and collide so violently that they overcome their natural electromagnetic repulsion and fuse together, creating helium and releasing tremendous amounts of energy in the process. This nuclear fusion is the same process that powers hydrogen bombs, but in the sun's core, it's happening at a rate that converts about 4 million tons of matter into pure energy every single second. That energy, born in the crushing depths of the sun's core, begins a journey that will take thousands of years to complete. The photons created by fusion don't simply race outward. They're trapped in an endless game of pinball, bouncing off particles, being absorbed and re-emitted countless times as they slowly work their way toward the surface. A single photon might travel for 10,000 years or more, ping-ponging through the sun's interior before finally escaping into space. When that energy finally reaches the sun's surface, it's traveling at the speed of light, and it takes just 8 minutes and 20 seconds to bridge the 93 million miles to Earth. Think about that for a moment. The sunlight warming your face right now began its journey in the sun's core when your ancestors were building the first cities, when woolly mammoths still roamed the Earth, when the last ice age was ending. The sun's surface, what we call the photosphere, is a roiling, turbulent sea of plasma at about 5,500 degrees Celsius. It's covered in granules, convection cells, where hot plasma rises and cool plasma sinks, creating a constantly shifting pattern that looks almost like the surface of boiling water when viewed through powerful telescopes. Each granule is about the size of Texas, and they appear and disappear on timescales of minutes. A constant reminder that our sun is a dynamic, ever-changing entity, but the sun's influence extends far beyond its visible surface. The solar wind, a stream of charged particles flowing outward from the sun, creates a bubble around our entire solar system called the heliosphere. This invisible boundary, stretching far beyond Pluto, is where the sun's influence finally gives way to the interstellar medium. We live inside this bubble, protected by our sun's embrace from the harsh radiation of deep space. The sun's magnetic field, generated by the complex dance of plasma in its interior, creates some of the most spectacular phenomena in our solar system. Solar flares, explosive releases of magnetic energy, can hurl particles into space at speeds approaching the speed of light. When these particles interact with Earth's magnetic field, they create the aurora borealis and aurora australis, those dancing curtains of light that paint the polar skies in green and red and purple. But the sun's magnetic field is not constant. It follows an 11-year cycle, growing stronger and weaker in a rhythm that affects everything from the frequency of solar flares to the number of sunspots on the sun's surface. During solar maximum, the sun's surface is peppered with dark sunspots, regions where magnetic field lines have become so tangled that they suppress the flow of hot plasma from below. During solar minimum, the sun's face becomes relatively smooth and quiet. This solar cycle has been observed and recorded for centuries, and it has subtle but measurable effects on Earth's climate, radio communications, and even the behavior of migrating animals. We're learning that the sun's variability, once thought to be negligible, actually plays a more significant role in Earth's climate system than previously understood. The sun's composition tells the story of our cosmic heritage. It's about 73% hydrogen, 25% helium, and 2% heavier elements, what astronomers call metals, though they include elements like oxygen, carbon, and iron. These heavier elements weren't present when the sun first formed 4.6 billion years ago. They were created in the hearts of earlier generations of stars, scattered into space when those stars died, and incorporated into the cloud of gas and dust that eventually collapsed to form our sun and solar system. In this sense, our sun is a third-generation star, enriched by the nuclear alchemy of its predecessors. The calcium in our bones, the iron in our blood, the oxygen we breathe, All of these elements were forged in the cores of ancient stars and distributed by their death throes. We are, quite literally, made of star stuff, and our sun is the stellar hearth around which this cosmic recycling has organized itself into the complexity we call life. The sun's energy output, about 3.8 times 10 to the 26th watts, is almost incomprehensibly vast. To put this in perspective, the sun produces more energy in 1 second than humanity has consumed in its entire history. This energy radiates outward in all directions, and Earth intercepts only about 1/2 billionth of it. Yet this tiny fraction is enough to power our weather systems, drive photosynthesis, and maintain the delicate thermal balance that keeps our planet habitable. But our sun won't shine forever. Like all stars, it has a finite lifespan, determined by the amount of hydrogen fuel in its core. We're currently about halfway through the sun's main sequence lifetime, the stable period when it fuses hydrogen into helium. In about 5 billion years, the sun will begin to exhaust its core hydrogen supply, and its nuclear fires will start to dim. When that happens, the sun will undergo a dramatic transformation. It will swell into a red giant star, expanding to perhaps 100 times its current size. The outer layers will become cool and red, while the core grows hotter and denser. During this phase, the sun will likely engulf Mercury and Venus, and Earth will be scorched by the intense radiation from the bloated stellar envelope. Eventually, the sun will shed its outer layers entirely, creating a beautiful planetary nebula, a glowing shell of gas expanding into space. What remains will be a white dwarf star about the size of Earth, but with half the mass of the current sun. This stellar remnant will slowly cool over trillions of years, eventually becoming a cold, dark cinder drifting through space. But that distant future shouldn't concern us now. We exist in the sun's golden age, when it burns steadily and reliably, providing the energy that powers the intricate dance of life on Earth. Every day, our sun rises and sets with clockwork precision, marking the passage of time and the rhythm of existence. This is just the beginning of our journey into the heart of our solar system. We've barely scratched the surface of what we know about our sun, its internal structure, its magnetic mysteries, its influence on space weather, and its role in the broader cosmic story. In the next part of our exploration, we'll delve deeper into the sun's interior, discovering the incredible journey that energy takes from the nuclear furnace of the core to the light that brightens our days. For now, take a moment to appreciate the star that makes everything possible. Whether you can see it shining outside your window or you're experiencing the gentle darkness it has gifted to your side of the world, remember that you're part of a story that began 4.6 billion years ago and will continue for billions of years to come. Our sun is not just a star, it's home. As we continue our gentle exploration of our cosmic companion, let's venture deeper into the sun's hidden architecture, the layers that lie beneath that brilliant surface we see each day. Think of the sun as a vast celestial onion, each layer with its own personality, its own story to tell about the incredible processes that keep our star burning bright. The journey begins at the very heart of our sun, in a region called the core. Here, in a space roughly the size of Jupiter, but containing about half of the sun's entire mass, the temperature soars to an almost unimaginable 27 million degrees Fahrenheit. The pressure is so intense that matter exists in a state completely foreign to our earthly experience. A plasma so dense that a teaspoon of it would weigh about 5 tons. In this extreme environment, the fundamental forces of nature engage in their most spectacular performance. Hydrogen nuclei, normally repelled by their positive electrical charges, are slammed together with such violence that they overcome their natural aversion and fuse into helium. This process, called nuclear fusion, is what makes the sun shine. Every second, 600 million tons of hydrogen are converted into helium, and in the process, 4 million tons of matter disappear entirely, transformed into pure energy according to Einstein's famous equation. But here's something remarkable that might surprise you. The core of our sun is actually less dense than lead. Despite the crushing pressure and searing heat, the plasma state of matter means that particles are more spread out than in the familiar solids and liquids we encounter on Earth. It's a paradox that speaks to the alien nature of stellar interiors, where the rules of physics create conditions unlike anything in our everyday experience. The energy created in the core begins an epic journey outward, but it's not the straightforward path you might expect. Surrounding the core is a region called the radiative zone, extending about 2/3 of the way to the sun's surface. Here, the temperature drops to a mere 2 million degrees, and the density decreases dramatically. In this zone, energy moves outward, not through the violent convection we see at the surface, but through radiation. Photons bouncing endlessly from particle to particle. This is where those ancient photons begin their millennia-long journey. A single photon created in the core might travel just a few millimeters before being absorbed by an atom, then re-emitted in a completely random direction. It's a cosmic game of chance, where each photon takes a random walk through the sun's interior, sometimes moving outward, sometimes sideways, sometimes even backward toward the core. The mathematics of this process are staggering. If a photon could travel in a straight line from the core to the surface, it would complete the journey in about 2 seconds. But the actual path, with all its random collisions and deflections, takes between 10,000 and 100,000 years. The sunlight that warmed the faces of ancient Egyptian pyramid builders, that illuminated the first Olympic Games, that witnessed the rise and fall of entire civilizations. That light was born in the sun's core during the last ice age. As we move outward from the radiative zone, we encounter the convection zone, where the sun's behavior changes dramatically. Here, the temperature has dropped to about 2 million degrees, and the plasma becomes opaque enough that radiation alone can no longer transport energy efficiently. Instead, the sun turns to convection, the same process that creates bubbles in boiling water, but on a scale that dwarfs our planet. Hot plasma rises from the depths like enormous bubbles, carrying energy toward the surface. When it reaches the photosphere, it cools and sinks back down, creating a continuous circulation pattern. These convection cells are truly massive. Some are the size of Earth, others larger than Jupiter. They churn and roil in a constant dance, creating the granular texture we see on the sun's surface through powerful telescopes. This convection zone is also where the sun's magnetic field is born. The churning plasma acts like a vast dynamo, with moving electrical charges creating magnetic fields that twist and tangle as they rise toward the surface. These magnetic field lines sometimes become so contorted that they break through the photosphere, creating the dark patches we call sunspots. Sunspots are actually cooler regions of the sun's surface, appearing dark only in contrast to the surrounding hotter plasma. They're temporary features, lasting anywhere from days to months, and they follow the sun's 11-year magnetic cycle. During solar maximum, the sun's surface can be peppered with dozens of sunspot groups, while during solar minimum, days or even weeks can pass without a single spot appearing. The study of sunspots has revealed something fascinating about our sun's rotation. Unlike Earth, which spins as a solid body, the sun rotates differentially. The equator completes a rotation in about 25 days, while the poles take about 35 days. This differential rotation is what drives the sun's magnetic dynamo, stretching and twisting magnetic field lines like rubber bands until they snap and reconnect in violent solar flares. Above the photosphere lies the chromosphere, a thin layer of the sun's atmosphere that's normally invisible to our eyes, but reveals itself during solar eclipses as a reddish glow around the sun's edge. The chromosphere is a region of transition where the temperature actually increases with altitude, a phenomenon that puzzled scientists for decades. We now understand that magnetic fields play a crucial role in heating this layer, channeling energy upward in ways that are still being studied. Beyond the chromosphere lies the corona, the Sun's outermost atmosphere, and perhaps its most mysterious layer. Visible during total solar eclipses as a shimmering white halo extending millions of kilometers into space, the corona is a place where the normal rules seem to break down. Despite being farther from the Sun's core than the photosphere, the corona is actually much hotter, reaching temperatures of over 1,000,000 degrees Celsius. This coronal heating problem has been one of the most enduring mysteries in solar physics. How can a region so far from the Sun's energy source be hundreds of times hotter than the visible surface? The answer lies in the Sun's magnetic field, which acts like a complex network of highways, channeling energy from the solar interior into the corona. Magnetic field lines twist and reconnect in explosive events, heating the surrounding plasma to incredible temperatures. The corona is also where the solar wind is born. This constant stream of charged particles flows outward from the Sun at speeds ranging from 300 to 800 kilometers per second, carrying with it the Sun's magnetic field and creating the heliosphere, the vast bubble of solar influence that surrounds our entire solar system. When the solar wind encounters Earth's magnetic field, it creates some of the most beautiful phenomena in our solar system. The aurora borealis and aurora australis, the northern and southern lights, are the result of solar wind particles being channeled by Earth's magnetic field into the polar regions, where they collide with atoms in our atmosphere and create those ethereal curtains of light. But the Sun's influence extends far beyond the beautiful auroras. Solar flares and coronal mass ejections can disrupt satellite communications, interfere with GPS systems, and even cause power grid failures on Earth. As our technological civilization becomes increasingly dependent on electronic systems, understanding space weather has become crucial for maintaining our modern way of life. The Sun's magnetic field also plays a role in protecting our solar system from galactic cosmic rays, high-energy particles from deep space that could be harmful to life. The heliosphere acts as a partial shield, deflecting some of these particles and reducing the radiation environment throughout the solar system. Recent space missions have revolutionized our understanding of the Sun's structure and behavior. The Parker Solar Probe, launched in 2018, is gradually spiraling closer to the Sun, eventually coming within 4 million miles of the surface, close enough to actually fly through the corona. The data it's collecting is helping us understand how the corona is heated and how the solar wind accelerates to its tremendous speeds. The Solar Dynamics Observatory, orbiting Earth, watches the Sun continuously in multiple wavelengths of light, revealing the dynamic nature of our star in unprecedented detail. We can now see solar flares erupting in real time, watch the formation and evolution of sunspots, and track the complex dance of magnetic field lines throughout the Sun's atmosphere. These observations have revealed that our Sun is far more variable and dynamic than we once believed. The old image of the Sun as a steady, unchanging source of light and heat has been replaced by our understanding of a star that's constantly evolving, with magnetic fields that twist and snap, plasma that churns and flows, and energy that pulses and varies on timescales from seconds to centuries. The Sun's internal structure tells us not just about our own star, but about stellar evolution throughout the universe. Our Sun is what astronomers call a population 1 star, relatively young and enriched with heavy elements from previous generations of stars. This composition is crucial for planet formation and, ultimately, for the development of life as we know it. The heavier elements in the Sun, that 2% of oxygen, carbon, iron, and other metals, were forged in the nuclear furnaces of massive stars that lived and died before our solar system formed. When these ancient stars exploded as supernovae, they scattered these precious elements into space, where they were eventually incorporated into the cloud of gas and dust that collapsed to form our sun and its planetary system. This cosmic recycling process means that every atom in your body, except for hydrogen, was once part of a star. The oxygen you breathe, the carbon that forms the backbone of organic molecules, the iron in your blood, all of these elements were created in stellar cores and distributed by stellar death. We are, in the most literal sense, children of the stars, and our sun is the hearth around which this stellar heritage has organized itself into the complexity we call life. As we continue to study our sun, we're discovering that it's not just a source of energy, but a complex system with its own weather patterns, seasonal cycles, and long-term climate variations. The sun's activity affects everything from Earth's climate to the behavior of comets in the outer solar system. Understanding these connections is helping us piece together the intricate web of relationships that bind our solar system together. The sun's story is also our story, the tale of how a cloud of gas and dust transformed into the system of worlds we call home. In the next part of our journey, we'll explore how the sun's birth shaped the formation of the planets, how its energy drives the processes that make Earth habitable, and how its future evolution will ultimately determine the fate of our world. For now, as you rest in the gentle embrace of evening or morning, remember that you're part of an ancient story written in the language of fusion and magnetic fields, of plasma and light. The sun above us is not just a star, it's the author of our existence, the conductor of our cosmic symphony, and the source of every sunset and sunrise that has ever painted the sky. The sun's influence on our daily lives runs deeper than most of us realize. As you sit here listening to these words, your body is responding to rhythms that were set in motion by our star billions of years ago. The circadian clock ticking away in your cells, the seasonal changes in your mood and energy levels, even the way your eyes have evolved to see the world. All of these are testament to the profound connection between life on Earth and the nuclear furnace that lights our days. Consider the remarkable precision of Earth's orbital dance around the sun. We circle our star at an average distance of 93 million miles, but this distance isn't constant. Earth's orbit is slightly elliptical, bringing us about 3 million miles closer to the sun in early January and 3 million miles farther away in early July. You might think this would create dramatic seasonal changes, but the effect is surprisingly subtle. The difference in solar energy received is only about 6%. The seasons we experience aren't caused by our changing distance from the sun, but by something far more elegant: the 23.5-degree tilt of Earth's axis. As our planet orbits the sun, this tilt means that different hemispheres receive more direct sunlight at different times of the year. When the northern hemisphere tilts toward the sun, we experience summer, while the southern hemisphere enjoys winter. 6 months later, the situation reverses. This axial tilt is likely the result of a cosmic collision that occurred early in Earth's history, when a Mars-sized object struck our forming planet with such force that it not only tilted our world, but also blasted debris into orbit that would eventually coalesce into the moon. It's a reminder that even the most fundamental aspects of our existence, the very rhythm of the seasons, can be traced back to ancient cosmic events. The sun's energy doesn't just warm our planet, it drives virtually every process that makes Earth habitable. When sunlight strikes the oceans, it evaporates water that rises into the atmosphere, condenses into clouds, and falls as rain, feeding rivers and lakes and groundwater systems. This water cycle, powered entirely by solar energy, is what makes liquid water available across our planet's surface. Solar energy also drives our weather systems. The uneven heating of Earth's surface, more intense at the equator than at the poles, creates temperature differences that generate winds. These winds, combined with the Coriolis effect created by Earth's rotation, produce the complex patterns of weather that shape our climate. Hurricanes, tornadoes, thunderstorms, and gentle breezes all trace their energy back to the nuclear fusion occurring in the sun's core. The sun's energy is also captured and stored by living organisms in a process we call photosynthesis. Plants, algae, and certain bacteria have evolved the remarkable ability to convert sunlight into chemical energy, creating the glucose that forms the foundation of virtually all food chains on Earth. The green chlorophyll in plants is essentially a biological solar panel, capturing photons and using their energy to split water molecules and combine carbon dioxide into organic compounds. This process does more than just create food. It's also responsible for the oxygen we breathe. Every breath you take contains oxygen molecules that were liberated from water by photosynthesis, using energy that originated in the sun's core. The oxygen in our atmosphere is not a natural feature of rocky planets. It's a byproduct of billions of years of solar-powered life. The fossil fuels that power our modern civilization are also stored solar energy. Coal, oil, and natural gas are the compressed remains of ancient plants and organisms that captured sunlight millions of years ago. When we burn these fuels, we're releasing solar energy that was stored in the geological past, concentrated over vast periods of time into the dense energy sources that built our industrial world. Even wind power and hydroelectric energy are indirect forms of solar power. Wind is created by the uneven heating of Earth's surface by the sun, while hydroelectric power depends on the water cycle that lifts water from the oceans to the mountains, again using solar energy. Only nuclear power, geothermal energy, and tidal energy operate independently of our sun's influence. The sun's activity also affects our planet in ways both subtle and dramatic. Solar flares and coronal mass ejections can disrupt radio communications, interfere with GPS satellites, and create spectacular auroral displays. But these space weather events can also have more serious consequences. In 1859, a massive solar storm called the Carrington event caused telegraph systems around the world to fail, with some operators receiving electric shocks and telegraph paper catching fire. In our modern world, heavily dependent on electronic systems, a similar event could have catastrophic consequences. Power grids could fail, satellites could be damaged, and our GPS-dependent transportation systems could be disrupted. Scientists continuously monitor the sun's activity, watching for signs of major solar storms that could threaten our technological infrastructure. The sun's magnetic field also plays a crucial role in protecting our solar system from galactic cosmic rays. These high-energy particles from deep space are deflected by the heliosphere, the vast bubble of solar influence that surrounds our planetary system. Without this protection, the radiation environment in our solar system would be much harsher, potentially making the evolution of complex life more difficult. Recent research has revealed that the sun's activity varies on multiple timescales, from the familiar 11-year sunspot cycle to longer-term variations that can last centuries. The Maunder minimum, a period from roughly 1645 to 1715, when very few sunspots were observed, coincided with particularly cold temperatures in Europe and North America, a period sometimes called the Little Ice Age. While the sun's variability is not the primary driver of current climate change that's clearly linked to human activities, it does contribute to natural climate variations. Understanding these solar influences helps scientists separate natural climate variability from human-caused changes, providing a more complete picture of how our planet's climate system works. The sun's influence extends throughout our solar system, creating a complex web of relationships that affects every world in our planetary family. The solar wind sculpts the magnetospheres of planets that have magnetic fields, while stripping away the atmospheres of worlds that don't. Mars, lacking a strong magnetic field, has gradually lost much of its atmosphere to the solar wind over billions of years. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are massive enough to retain their atmospheres despite the solar wind, but their great distances from the sun mean they receive much less solar energy. Jupiter receives only about 4% of the solar energy that Earth does, while Neptune, at the edge of our solar system, receives less than 0.1%. This decrease in solar energy with distance is why the outer planets are so cold. The moons of Jupiter and Saturn, despite being warmed by tidal heating from their parent planets, are frozen worlds where water exists primarily as ice. Yet even in these cold, distant realms, the sun's energy plays a role in shaping weather patterns and seasonal changes. The sun's gravitational influence is what holds our entire solar system together. Its massive pull keeps the planets in their orbits, prevents them from flying off into interstellar space, and maintains the delicate balance that has allowed stable planetary orbits for billions of years. Even the most distant objects in our solar system, the comets in the Oort cloud, perhaps a light year away, are still bound by the sun's gravitational embrace. As we develop new technologies to study the sun, we're discovering that our star is even more complex and dynamic than we previously imagined. The Solar Dynamics Observatory captures images of the sun every 12 seconds in multiple wavelengths of light, revealing the constant motion and evolution of our star's surface and atmosphere. We can watch plasma flows, magnetic field lines, and energy releases in real time, building a more complete picture of how our sun works. The Parker Solar Probe, humanity's first mission to touch the sun, is providing unprecedented insights into the corona and solar wind. By flying through the sun's outer atmosphere, it's measuring conditions that we could previously only observe from a distance. The data it's collecting is helping us understand how the corona is heated to its incredible temperatures and how the solar wind accelerates to its tremendous speeds. Future missions will continue to expand our understanding of the sun. The European Space Agency's Solar Orbiter is studying the sun's polar regions, areas we've never been able to observe directly from Earth. These high-latitude observations are crucial for understanding the sun's magnetic field and how it evolves over the solar cycle. The sun's story is intimately connected to the story of life on Earth. The gradual increase in solar luminosity over billions of years has driven the evolution of our planet's atmosphere and climate. When the sun first formed, it was about 30% dimmer than it is today. Earth should have been frozen solid, yet we know that liquid water existed on our planet's surface even then. This apparent contradiction, known as the faint young sun paradox, is still not fully resolved. The most likely explanation is that Earth's early atmosphere contained much higher levels of greenhouse gases, particularly carbon dioxide and methane, which trapped enough heat to keep the planet warm despite the weaker sun. As the sun gradually brightened over geological time, these greenhouse gas levels decreased, maintaining relatively stable temperatures. This long-term interaction between solar evolution and atmospheric chemistry demonstrates how interconnected the sun and Earth systems truly are. Our planet's climate is not just influenced by solar activity on short timescales, but by the slow, steady evolution of the sun itself over billions of years. The sun's future evolution will ultimately determine the fate of Earth and all life on it. As we mentioned earlier, in about 5 billion years, the sun will begin to run out of hydrogen fuel in its core. When this happens, the delicate balance that has maintained the sun's steady output for billions of years will be disrupted. The sun will begin to expand, becoming a red giant star. During this phase, it will grow so large that it may engulf the inner planets, including Earth. Even if our planet survives this expansion, it will be scorched by the intense radiation from the bloated solar surface. The oceans will boil away, the atmosphere will be stripped into space, and Earth will become a barren, lifeless world. But this distant future shouldn't diminish our appreciation for the present. We exist during the sun's golden age, when it burns steadily and reliably, providing the energy that powers the magnificent complexity of life on Earth. Every sunrise is a reminder of the nuclear processes that make our existence possible. Every sunset, a testament to the orbital mechanics that regulate our days and seasons. The sun has been shining for 4.5 billion years, and it will continue to shine for another 5 billion years. In the context of cosmic time, human civilization is just a brief moment in the sun's story, yet it's a moment filled with unprecedented meaning. For the first time in the sun's long history, matter organized by its energy has become conscious, has developed the ability to study its source, and has begun to understand the processes that created it. We are the sun's way of knowing itself, the universe's way of understanding its own workings. Through our telescopes and spacecraft, our equations and theories, we are slowly unraveling the mysteries of the star that made us possible. In studying the sun, we are not just learning about nuclear physics and plasma dynamics and magnetic fields. We are discovering our own origins, our place in the cosmos, and the intricate web of relationships that connect us to the stars. The sun's light that reaches your eyes as you read these words began its journey in the core of our star, traveled for thousands of years through the solar interior, raced across 93 million miles of space in just 8 minutes, and now carries information that allows you to contemplate the very processes that created it. In this moment, you are part of an ancient conversation between matter and energy, between the nuclear furnace of the sun and the complex chemistry of consciousness. The sun's magnetic field is perhaps one of its most fascinating and least understood aspects. Unlike Earth's relatively simple dipolar magnetic field, with its north and south poles, the sun's magnetic field is a complex, ever-changing tapestry that defies easy description. It's generated by the movement of electrically charged plasma deep within the sun's convection zone, where hot material rises and cool material sinks in massive circulation patterns. This magnetic field doesn't exist in isolation. It's intimately connected to nearly every phenomenon we observe on the sun's surface. The dark sunspots that appear and disappear follow the magnetic field's 11-year cycle, growing in number as the field strengthens and vanishing as it weakens. But the cycle isn't just about quantity, it's about polarity reversal. Every 11 years, the sun's magnetic field completely flips, with the north and south magnetic poles switching places. What makes this particularly intriguing is that the full magnetic cycle actually takes 22 years to complete. After the first 11-year reversal, the sun must flip again to return to its original polarity. This means that the sunspot cycle we observe is actually just half of a much longer magnetic rhythm that pulses through our star like a slow cosmic heartbeat. The magnetic field lines that emerge from the sun's interior become twisted and tangled by the differential rotation we mentioned earlier. Imagine stretching a rubber band and then twisting it. Eventually it will snap back violently. The sun's magnetic field lines do something similar, but when they reconnect, they release enormous amounts of energy in the form of solar flares and coronal mass ejections. These magnetic storms can be spectacular to observe from a safe distance. A single solar flare can release more energy than billions of hydrogen bombs exploding simultaneously. The largest flares, classified as X-class events, can send streams of high-energy particles racing across the solar system at speeds approaching 1/3 the speed of light. When these particles reach Earth, they can create auroras visible as far south as the Caribbean and as far north as the Arctic Circle. But the sun's magnetic field isn't just about dramatic eruptions. It also plays a crucial role in the quieter aspects of solar behavior. The magnetic field helps to channel the flow of energy from the sun's interior to its surface, creating the complex patterns of hot and cool regions that we observe. It also influences the formation of the solar wind, guiding charged particles as they escape from the sun's gravitational grip and stream outward into space. Recent observations have revealed that the sun's magnetic field extends far beyond what we previously imagined. The solar wind carries magnetic field lines with it as it flows outward, creating what scientists call the interplanetary magnetic field. This field, though incredibly weak by Earth standards, influences the behavior of cosmic rays, affects the orbits of spacecraft, and even plays a role in the formation of the tails of comets. The study of the sun's magnetic field has also revealed something unexpected about our star's interior structure. The boundary between the radiative zone and the convection zone, called the tachocline, appears to be where the sun's magnetic field is generated. This thin layer, where the sun's rotation changes from the rigid rotation of the interior to the differential rotation of the surface, acts like a massive dynamo, converting the kinetic energy of moving plasma into magnetic energy. Understanding the sun's magnetic field is crucial for predicting space weather and protecting our technological infrastructure. As our civilization becomes increasingly dependent on satellites, GPS systems, and electronic communications, the ability to forecast solar storms becomes ever more important. Scientists are working to develop better models of the sun's magnetic behavior, using observations from multiple spacecraft and ground-based telescopes to track the evolution of magnetic field lines from the sun's surface out into the solar system. The sun's influence on Earth's climate extends far beyond the simple heating effect of its radiation. The varying intensity of the solar wind, driven by changes in the sun's magnetic field, affects the number of cosmic rays that reach Earth's atmosphere. These cosmic rays may play a role in cloud formation, potentially creating a subtle but measurable influence on Earth's weather patterns. While this effect is small compared to other climate drivers, it demonstrates the intricate ways in which our star's behavior ripples through the Earth system. The sun's magnetic field also protects our solar system from the harsh radiation environment of interstellar space. The heliosphere, that vast bubble of solar influence, is shaped by the interaction between the solar wind and the magnetic field of the galaxy itself. At the heliopause, the boundary where the solar wind meets the interstellar medium, the sun's magnetic field helps to deflect some of the high-energy particles that would otherwise flood our solar system. Voyager 1 and Voyager 2, those intrepid spacecraft launched in the 1970s, have now crossed this boundary and are sending back data from interstellar space. Their measurements are helping us understand how the sun's magnetic field interacts with the galaxy's magnetic field, providing insights into the broader cosmic environment in which our solar system resides. The sun's magnetic field also influences the formation and evolution of planets. During the early stages of our solar system's formation, the young sun's magnetic field helped to clear away the remaining gas and dust from the solar nebula, ending the period of rapid planetary accretion. This magnetic braking effect may have played a crucial role in determining the final sizes and compositions of the planets we observe today. Even now, the sun's magnetic field continues to shape our solar system. The solar wind and its embedded magnetic field interact with the magnetic fields of planets, creating the magnetospheres that protect worlds like Earth from the harsh radiation environment of space. Planets without strong magnetic fields, like Mars, have gradually lost much of their atmospheres to the solar wind over billions of years. The sun's magnetic field is also responsible for some of the most beautiful phenomena in our solar system. The aurora borealis and aurora australis are created when charged particles from the solar wind, guided by the sun's magnetic field, interact with Earth's magnetic field and atmosphere. These dancing curtains of light are a visible manifestation of the invisible magnetic connections that link our planet to our star. As we continue to study the sun's magnetic field, we're discovering that it's even more complex and dynamic than we previously realized. New observations reveal magnetic field lines that stretch and snap like cosmic rubber bands, creating loops and arches that rise from the sun's surface and extend millions of kilometers into space. These magnetic structures are constantly evolving, driven by the churning motions of the sun's convective interior. The sun's magnetic field also plays a crucial role in the formation of its corona, that mysterious outer atmosphere that's hundreds of times hotter than the visible surface. The magnetic field lines act like invisible highways, channeling energy from the sun's interior into the corona and heating it to its incredible temperatures. Understanding this process is one of the key goals of current solar research, as it could help us predict and mitigate the effects of solar storms on Earth. The Sun's magnetic field is not static. It's constantly evolving, responding to the complex dynamics of the solar interior. During periods of high magnetic activity, the Sun's surface becomes a chaotic landscape of magnetic field lines that twist and tangle, creating the conditions for powerful solar flares and coronal mass ejections. During periods of low activity, the magnetic field becomes more organized and stable, creating the quiet conditions that allow us to observe the Sun's more subtle behaviors. This variability has implications that extend far beyond our solar system. Other stars throughout the galaxy also have magnetic fields, and by studying our Sun's magnetic behavior, we're learning about the magnetic activity of stars in general. This knowledge is crucial for understanding the habitability of exoplanets, as the magnetic activity of their host stars can dramatically affect the atmospheric evolution and potential for life on these distant worlds. The Sun's magnetic field is also a window into the fundamental processes that govern stellar evolution. As the Sun ages and its internal structure changes, its magnetic field will evolve as well. The magnetic cycles that we observe today may change in intensity and duration as the Sun gradually exhausts its hydrogen fuel and begins its transformation into a red giant star. Future missions to study the Sun will provide even more detailed insights into its magnetic behavior. The Parker Solar Probe, flying closer to the Sun than any previous spacecraft, is measuring the magnetic field directly in the corona, providing unprecedented data about how magnetic energy is converted into the heat that makes the corona so hot. The Solar Orbiter mission is studying the Sun's polar regions, areas that are crucial for understanding the global structure of the Sun's magnetic field. These observations are helping us build more accurate models of the Sun's magnetic behavior, which in turn will improve our ability to predict space weather and protect our technological infrastructure. As we become an increasingly spacefaring civilization, with missions to the Moon, Mars, and beyond, understanding the Sun's magnetic field becomes ever more important for protecting astronauts and spacecraft from the harsh radiation environment of space. The Sun's magnetic field is a reminder of the dynamic, ever-changing nature of our star. Far from being a simple ball of burning gas, the Sun is a complex magnetic entity whose behavior affects every corner of our solar system. Its magnetic field connects us to our star in ways both subtle and profound, influencing everything from the auroras that dance in our polar skies to the cosmic rays that rain down on our atmosphere. As you rest tonight, perhaps you can imagine the invisible magnetic field lines that stretch from the Sun's surface all the way to the edge of our solar system, creating a vast network of magnetic connections that link every world in our planetary family. These field lines are constantly moving, constantly evolving, constantly carrying the Sun's influence to the farthest reaches of its domain. The Sun's magnetic field is also a bridge between the microscopic and the cosmic. The same quantum mechanical processes that govern the behavior of individual atoms also operate on the scale of our entire star, creating magnetic fields that span millions of kilometers. In studying the Sun's magnetism, we're exploring the fundamental forces that shape matter and energy throughout the universe. The Sun's magnetic field tells us that our star is not just a source of light and heat, but a complex, dynamic system whose behavior ripples through space and time. It's a reminder that we live in a universe where everything is connected, where the nuclear fires burning in the Sun's core create magnetic fields that influence the behavior of particles and planets throughout our solar system. This magnetic connection between the Sun and Earth is ancient and ongoing. For billions of years, the Sun's magnetic field has been shaping our planet's environment, protecting us from cosmic radiation and creating the conditions that allowed life to flourish. It's a relationship that will continue for billions of years to come, as the sun's magnetic field evolves and changes with the slow rhythm of stellar time. The sun's magnetic field is perhaps the most visible manifestation of the invisible forces that govern our universe. Through its study, we're learning not just about our own star, but about the fundamental processes that create structure and order throughout the cosmos. It's a field of study that bridges physics and astronomy, connecting the behavior of subatomic particles to the evolution of entire stellar systems. As we continue to unravel the mysteries of the sun's magnetic field, we're discovering that it's even more beautiful and complex than we ever imagined. It's a cosmic symphony played out in magnetic field lines and plasma flows, a dance of energy and matter that has been ongoing for billions of years and will continue long after we're gone. The sun's magnetic field is a testament to the power of observation and scientific inquiry. Through careful study and measurement, we've been able to map the invisible architecture of our star, revealing the hidden forces that drive its behavior. It's a reminder that the universe is full of wonders waiting to be discovered, phenomena that challenge our understanding and expand our knowledge of the cosmos. The sun's magnetic field connects us to the stars in ways both literal and metaphorical. The same magnetic processes that operate in our sun also occur in stars throughout the galaxy, creating a common thread that links our solar system to the broader universe. In studying the sun's magnetism, we're learning about the magnetic behavior of stars in general, expanding our understanding of stellar evolution and the conditions that make planetary systems possible. The sun's magnetic field is also a source of inspiration and wonder. The invisible lines of force that emanate from our star remind us that the universe is full of phenomena that operate beyond the reach of our direct senses. Through the tools of science and the power of human curiosity, we're able to reveal these hidden aspects of reality, expanding our perception of the cosmos and our place within it. The sun's magnetic field is also responsible for one of the most remarkable discoveries in modern solar physics, the existence of magnetic tornadoes. These towering spirals of plasma, some reaching heights of thousands of kilometers, twist and spiral along magnetic field lines like cosmic whirlwinds. Unlike earthly tornadoes, which are driven by atmospheric pressure differences, these solar tornadoes are guided by the invisible architecture of magnetism, creating structures that can dwarf our entire planet. These magnetic tornadoes aren't just spectacular to observe. They may be one of the key mechanisms by which energy is transported from the sun's interior to its corona. As plasma spirals along the magnetic field lines, it carries heat and energy upward, contributing to the mysterious process that makes the corona so much hotter than the layers beneath it. It's another example of how the sun's magnetic field serves as both sculptor and conductor, shaping the flow of matter and energy throughout our star's atmosphere. The dance between the sun's magnetic field and its plasma creates what scientists call magnetic reconnection, a process so fundamental to solar behavior that it deserves our careful attention. Imagine two garden hoses, each carrying water under pressure. If you were to suddenly connect them, the water would rush from one to the other, seeking equilibrium. Magnetic reconnection works similarly, but instead of water, it's magnetic field lines that suddenly connect, releasing enormous amounts of stored energy in the process. This reconnection can happen anywhere on the sun, where magnetic field lines of opposite polarity come close together. When they connect, they create a kind of magnetic short circuit, converting magnetic energy into kinetic energy and heat with explosive force. The result can be a solar flare that releases more energy in minutes than humanity has consumed in its entire history, or a coronal mass ejection that hurls billions of tons of plasma into space at speeds of millions of miles per hour. But the sun's magnetic field doesn't just create dramatic explosions. It also maintains quieter, more subtle structures that are equally fascinating. Magnetic field lines can form stable loops that arch gracefully from the sun's surface, creating what astronomers call prominences. These vast curtains of relatively cool plasma, suspended in the sun's hot corona by magnetic forces, can persist for days or even weeks. slowly evolving as the magnetic field beneath them changes. When viewed from Earth during a solar eclipse, prominences appear as delicate pink flames dancing along the sun's edge. But their apparent delicacy is deceptive. Each prominence contains enough plasma to fill thousands of volumes the size of Earth. They're held aloft by magnetic forces so precisely balanced that they seem to defy gravity, floating in the corona like cosmic clouds made of fire. The sun's magnetic field also creates more temporary structures called spicules, narrow jets of plasma that shoot upward from the sun's surface like grass growing at tremendous speed. These spicules, only a few hundred kilometers wide but extending thousands of kilometers into the corona, last for just minutes before fading away. Yet they're constantly forming and dissolving across the sun's surface, creating a dynamic forest of plasma jets that may play a crucial role in heating the corona. Recent high-resolution observations have revealed that the sun's surface is far more dynamic than we ever imagined. The magnetic field creates a constantly changing landscape of bright points, dark lanes, and swirling patterns that shift and evolve on timescales of minutes. It's as if the sun's surface is covered with a layer of magnetic weather, with storms and calm regions that come and go like clouds passing overhead. This magnetic weather affects the sun's energy output in subtle but measurable ways. During periods of high magnetic activity, the sun's surface becomes covered with magnetic structures that can either increase or decrease the amount of energy radiated into space. The net effect is small, less than 1%, but it's enough to influence Earth's climate over long periods. Ice ages and warm periods in Earth's history may be partly linked to these long-term variations in the sun's magnetic activity. The sun's magnetic field also influences the formation and behavior of solar wind streams. Fast-moving streams of solar wind originate from regions where the magnetic field lines are open, extending far into space rather than looping back to the sun's surface. These open field regions, called coronal holes, appear as dark areas in X-ray images of the sun because they're cooler and less dense than the surrounding corona. When these fast solar wind streams reach Earth, they can trigger geomagnetic storms that disrupt our planet's magnetic field and create spectacular auroral displays. The interaction between the solar wind and Earth's magnetosphere is like a cosmic dance, with the sun leading and Earth following, responding to every change in the solar wind's speed and magnetic orientation. The sun's magnetic field extends its influence throughout our solar system in ways that are both obvious and subtle. The magnetic field embedded in the solar wind creates the interplanetary magnetic field, which affects the trajectories of cosmic rays, influences the formation of comet tails, and even plays a role in the erosion of planetary atmospheres. Mars, lacking a strong magnetic field of its own, has gradually lost much of its atmosphere to the solar wind over billions of years. Jupiter's enormous magnetic field, generated by the motion of metallic hydrogen in its interior, creates a magnetosphere so large that it would appear as big as the full moon if we could see it from Earth. When the solar wind encounters this magnetosphere, it compresses it on the sunward side and stretches it into a long tail on the opposite side. The interaction between Jupiter's magnetic field and the solar wind creates some of the most intense radiation environments in our solar system. Saturn's magnetic field, while weaker than Jupiter's, still creates a substantial magnetosphere that interacts with the planet's magnificent ring system. The magnetic field helps to confine charged particles within the magnetosphere, creating radiation belts that can damage spacecraft and affect the behavior of Saturn's moons. The aurora that dance around Saturn's poles, captured in stunning detail by the Cassini spacecraft, are created by the same magnetic processes that create Earth's northern and southern lights. Even the sun's magnetic field has a memory. The magnetic field lines that emerge from the sun's interior carry information about the conditions deep within our star. By studying the patterns of magnetic field emergence over time, scientists can learn about the dynamo processes operating in the sun's convection zone, gaining insights into the fundamental mechanisms that generate stellar magnetic fields. The sun's magnetic field is also a tool for understanding other stars throughout the galaxy. Many stars exhibit magnetic activity similar to our sun, with stellar flares, coronal mass ejections, and magnetic cycles that can be detected and studied from Earth. By comparing the magnetic behavior of different stars, astronomers are learning about the relationship between stellar mass, age, and magnetic activity. Some stars are much more magnetically active than our sun, producing flares thousands of times more powerful than anything our sun has ever generated. These magnetic monsters, often called flare stars, create radiation environments so harsh that they would likely sterilize any planets orbiting nearby. The study of these extreme magnetic stars helps us appreciate the relative stability of our own sun and the benign conditions it has maintained for billions of years. Other stars show magnetic cycles similar to our sun's 11-year cycle, but with different periods and intensities. Some stars have magnetic cycles that last decades, while others seem to have cycles that are much shorter or more irregular. These observations are helping astronomers understand the factors that control stellar magnetic behavior and how magnetic activity evolves over a star's lifetime. The sun's magnetic field is also crucial for understanding the formation of planetary systems. During the early stages of stellar evolution, strong magnetic fields can help clear away the remaining gas and dust from the protoplanetary disk, ending the period of rapid planet formation. The magnetic field can also influence the migration of planets, potentially affecting the final architecture of planetary systems. Recent observations of young stars have revealed that many of them have much stronger magnetic fields than our sun, with magnetic activity levels that would be catastrophic for life as we know it. As these stars age and their rotation slows, their magnetic activity typically decreases, eventually reaching the more moderate levels we observe in our sun today. This evolution of magnetic activity may be one of the factors that determines when a star becomes suitable for hosting habitable planets. The sun's magnetic field is also a window into the future evolution of our star. As the sun ages and its internal structure changes, its magnetic field will evolve as well. The magnetic cycles that we observe today may become weaker or more irregular as the sun gradually exhausts its hydrogen fuel and begins its transformation into a red giant star. During the red giant phase, the sun's magnetic field will likely become much weaker and more chaotic as the star's outer layers expand and cool. The solar wind will become slower and less dense, and the heliosphere will shrink, potentially exposing the outer planets to increased levels of cosmic radiation. The magnetic protection that has shielded our solar system for billions of years will gradually weaken as our star enters its final evolutionary stages, but these changes are still billions of years in the future. For now, the sun's magnetic field continues to evolve and change on much shorter timescales, creating the dynamic, ever-changing environment that makes our star so fascinating to study. Each solar cycle brings new patterns of magnetic activity, new configurations of field lines, and new opportunities to understand the complex processes that govern stellar magnetism. The sun's magnetic field is also a reminder of the interconnectedness of all things in our solar system. The magnetic field lines that emerge from our star create an invisible web that connects every planet, every moon, every comet, and every grain of dust in our cosmic neighborhood. We live within this magnetic web, influenced by its changes and protected by its embrace. As you prepare for rest tonight, perhaps you can imagine these invisible magnetic field lines stretching from the sun's surface all the way to the edge of our solar system, creating a vast network of connections that link our star to every corner of its domain. These field lines are constantly moving, constantly evolving, constantly carrying the sun's influence to the farthest reaches of space. The sun's magnetic field is one of the most beautiful and complex phenomena in our solar system, a testament to the power of invisible forces to shape the visible world. Through its study, we're learning not just about our own star, but about the fundamental processes that govern the behavior of matter and energy throughout the universe. It's a field of study that continues to surprise and delight us, revealing new wonders with each observation and each new mission to study our remarkable star. The sun's magnetic field connects us to the cosmos in ways both profound and practical. It protects us from cosmic radiation, creates the auroras that light our polar skies, and drives the space weather that affects our technological civilization. It's a reminder that we live in a universe where invisible forces play crucial roles in shaping the world we see and experience. In the gentle darkness of night, when the sun's light has faded from our corner of the world, the magnetic field continues its work, stretching across space like invisible threads that connect us to our star. Tomorrow, when the sun rises again, it will bring with it not just light and heat, but the ongoing influence of magnetic forces that have been shaping our solar system for billions of years and will continue to do so for billions more. The sun's magnetic field is a bridge between the seen and the unseen, between the familiar warmth of sunlight and the exotic physics of plasma and magnetic reconnection. It's a phenomenon that operates on scales from the subatomic to the cosmic, connecting the quantum world of individual particles to the vast architecture of our solar system. In studying the sun's magnetism, we're exploring one of the most fundamental forces in the universe, a force that shapes everything from the smallest atoms to the largest structures in space. As we continue our journey through the sun's many mysteries, we carry with us the knowledge that our star is far more than a simple source of light and heat. It's a complex, dynamic, magnetic entity whose influence extends throughout our solar system and beyond. The sun's magnetic field is just one aspect of this complexity, but it's an aspect that touches every corner of our cosmic neighborhood, creating connections and influences that we're only beginning to understand. The sun's magnetic field reminds us that the universe is full of invisible wonders, phenomena that operate beyond the reach of our direct senses, but profoundly influence the world we inhabit. Through the power of scientific observation and human curiosity, we're able to reveal these hidden aspects of reality, expanding our understanding of the cosmos and our place within it. The sun's magnetic field is a testament to the beauty and complexity of the natural world, a phenomenon that continues to inspire and challenge us as we seek to understand our place in the vast tapestry of space and time. The sun's energy production is a story of transformation that spans scales almost impossible to comprehend. Deep within the core, where temperatures reach 15 million degrees Celsius, 4 hydrogen nuclei undergo a cosmic dance that has been choreographed by the laws of physics for billions of years. This process, called the proton-proton chain reaction, is elegantly simple in concept, yet staggeringly complex in execution. The dance begins when 2 protons, hydrogen nuclei, collide with such tremendous force that they overcome the electrical repulsion that normally keeps them apart. In that moment of collision, something remarkable happens. One of the protons transforms into a neutron, releasing a positron and a neutrino in the process. The remaining proton and the newly formed neutron bind together, creating deuterium, a heavy isotope of hydrogen. This deuterium nucleus then collides with another proton, forming helium-3 and releasing a gamma-ray photon. Finally, 2 helium-3 nuclei collide and fuse, creating helium-4 and releasing 2 protons back into the cosmic reactor. The net result is that 4 hydrogen nuclei have been converted into 1 helium nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. But here's the crucial detail that makes this process so remarkable. The helium nucleus that emerges from this fusion reaction has slightly less mass than the 4 hydrogen nuclei that went into creating it. That missing mass, about 0.7% of the original mass, hasn't simply disappeared. It has been converted into pure energy according to Einstein's famous equation, EmC2, where even a tiny amount of mass, m, multiplied by the speed of light squared, c2, yields an enormous amount of energy, E. The scale of this energy production is breathtaking. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process, 4 million tons of matter are transformed into pure energy. To put this in perspective, if you could somehow capture just 1 second's worth of the sun's energy output, it would be enough to power human civilization at current consumption levels for about 500,000 years. The energy released in each fusion reaction is carried away primarily by gamma-ray photons, the most energetic form of light. These photons begin their journey toward the sun's surface immediately, but their path is anything but direct. The sun's interior is incredibly dense, packed with particles that constantly absorb and re-emit these photons. Each time a photon is absorbed, the atom that absorbs it becomes excited and then releases the energy as a new photon, often in a completely different direction. This creates what physicists call a random walk. The photon moves a short distance, gets absorbed, gets re-emitted in a random direction, moves another short distance, and the process repeats. The average distance a photon travels before being absorbed is only about a centimeter, yet the sun's radius is nearly 700,000 kilometers. This means that a single photon will be absorbed and re-emitted millions of billions of times before it finally escapes into space. The mathematics of this random walk process reveal something extraordinary about the timescales involved. While a photon traveling in a straight line could traverse the sun's radius in just 2.3 seconds, the actual random walk journey takes somewhere between 10,000 and 100,000 years. This means that the sunlight warming your face right now was created in the sun's core when human civilization was just beginning to develop agriculture, when the last ice age was ending, when our ancestors were first learning to work with metal. As these ancient photons make their way outward, they undergo a gradual transformation. The gamma rays created in the core are gradually absorbed and re-emitted at lower energies, slowly shifting from gamma rays to X-rays to ultraviolet light, and finally to the visible light and infrared radiation that we observe at the sun's surface. By the time they reach the photosphere, these photons have been completely transformed, carrying the same energy that was created in the core, but now distributed across a much broader spectrum of wavelengths. This energy transport process reveals something profound about the sun's structure. The inner 70% of the sun's radius is dominated by radiative energy transport, where photons carry energy outward through their long random walk. But in the outer 30%, the sun's opacity becomes so high that radiation alone cannot efficiently transport energy. Here, the sun turns to convection, the same process that creates bubbles in boiling water. In the convection zone, hot plasma rises from the depths like enormous bubbles, carrying energy toward the surface. When this plasma reaches the photosphere, it cools and radiates energy into space, then sinks back down to be reheated and begin the cycle again. These convection cells are truly massive. Some are the size of Earth, others larger than Jupiter. They create the granular texture we observe on the sun's surface through powerful telescopes, with bright centers where hot plasma is rising and dark edges where cooler plasma is sinking. The transition between the radiative zone and the convection zone, called the tachocline, is one of the most important regions in the sun's interior. Here, the rigid rotation of the inner sun gives way to the differential rotation of the outer layers, creating shear forces that help generate the sun's magnetic field. The tachocline is like a cosmic dynamo, converting the kinetic energy of the sun's rotation into magnetic energy that shapes much of the sun's behavior. The energy that finally escapes from the sun's surface carries with it information about the nuclear processes occurring in the core. By studying the spectrum of sunlight, the precise wavelengths of light that the sun emits, scientists can determine the temperature, density, and composition of different layers in the sun's atmosphere. The dark absorption lines in the solar spectrum, first observed by Joseph von Fraunhofer in the early 1800s, reveal the presence of dozens of different elements in the sun's outer layers. These spectral lines also reveal something remarkable about the sun's motion. The Doppler effect, which causes the pitch of a siren to change as it approaches and then recedes from you, also affects light. When part of the sun's surface is moving toward us, the light it emits is shifted slightly toward the blue end of the spectrum. When it's moving away, the light is shifted toward the red end. By measuring these tiny shifts in the wavelengths of spectral lines, astronomers can map the motion of gas on the sun's surface and even probe the interior through the technique of heliosismology. The sun rings like a bell, with sound waves generated by the turbulent convection in the outer layers. These waves travel through the sun's interior, bouncing off the core and returning to the surface, where they create tiny oscillations that can be detected by sensitive instruments. By studying the frequencies and patterns of these oscillations, scientists can map the sun's internal structure with remarkable precision, revealing details about the temperature, density, and composition of regions that will never be directly observable. The energy output of the sun is remarkably constant, varying by less than 0.1% over the course of the 11-year solar cycle. This stability is crucial for life on Earth, as it provides a steady energy source that has allowed complex ecosystems to develop and thrive. But the sun's output hasn't always been the same. When the sun first formed 4.6 billion years ago, it was about 30% dimmer than it is today. This gradual brightening, known as the faint young sun paradox, poses interesting questions about Earth's early climate and the conditions that allowed life to emerge. The sun's luminosity will continue to increase slowly over the next billion years, eventually making Earth too hot for liquid water to exist on its surface. But this change is so gradual that it's barely perceptible on human timescales. The sun's energy output is governed by the rate of nuclear fusion in its core, which depends on the temperature and density of the core material. As the sun ages and accumulates more helium in its core, the core becomes slightly more compressed, increasing the fusion rate and brightening the sun. The neutrinos produced alongside the gamma rays in the sun's core provide a unique window into the nuclear processes occurring deep within our star. Unlike photons, which interact strongly with matter and take thousands of years to escape the sun, neutrinos barely interact with matter at all. They stream out of the sun's core at nearly the speed of light, reaching Earth in just 8 minutes and providing real-time information about the fusion reactions occurring in the solar interior. Detecting these solar neutrinos requires enormous underground detectors filled with specially chosen materials that can capture the occasional neutrino interaction. The Sudbury Neutrino Observatory in Canada, the Super Kamiokande detector in Japan, and other facilities around the world have been studying solar neutrinos for decades, confirming our understanding of the nuclear processes that power the sun and providing insights into the fundamental properties of neutrinos themselves. The energy production in the sun's core is so efficient that it can maintain its current rate of fusion for about 10 billion years, using only the hydrogen in its core. We're currently about halfway through this main sequence lifetime, meaning the sun will continue to shine steadily for another 5 billion years. This longevity is one of the key factors that has allowed life to evolve on Earth. Unlike more massive stars that burn through their fuel in millions of years, the sun's modest mass ensures a long, stable lifetime that provides the steady energy input necessary for biological evolution. The sun's energy production also demonstrates the incredible efficiency of nuclear fusion as an energy source. The fusion of hydrogen into helium converts about 0.7% of the mass into energy, making it far more efficient than any chemical reaction. This efficiency is what allows the sun to produce such enormous amounts of energy while consuming a relatively small amount of its mass. If the sun were powered by chemical reactions instead of nuclear fusion, it would have exhausted its fuel supply in just a few thousand years. The energy transport mechanisms within the sun create a complex internal structure that varies dramatically with depth. In the core, the temperature and pressure are so extreme that matter exists in a state unlike anything found on Earth. The density is about 150 times that of water, yet the material is completely ionized plasma. Moving outward, the temperature and density decrease, but the material remains in the plasma state throughout most of the sun's interior. The boundary between the core and the radiative zone isn't sharp, but represents a gradual transition where the nuclear fusion rate decreases with distance from the center. About 99% of the sun's energy is generated within the inner 25% of its radius, with the fusion rate dropping rapidly as you move outward. This concentration of energy production in the core is what creates the extreme temperature gradient that drives energy transport throughout the rest of the sun. The convection zone, where hot plasma rises and cool plasma sinks, creates a completely different environment from the radiative zone below. Here, the energy transport is much more efficient, with hot material physically carrying energy upward rather than relying on the slow radiative diffusion process. This efficiency is what allows the sun to maintain its surface temperature despite the enormous energy flux coming from the interior. The granulation pattern visible on the sun's surface is a direct manifestation of these convection cells. Each granule represents the top of a convection cell, where hot plasma from the interior rises to the surface, radiates energy into space, and then cools and sinks back down. The typical granule is about 1,000 kilometers across and lasts for about 10 minutes before being replaced by a new cell. The constant formation and dissolution of these granules creates the dynamic, ever-changing texture of the sun's surface. The sun's energy production is also intimately connected to its magnetic field generation. The convection zone is where the sun's magnetic field is created through the dynamo process, as the motion of electrically conducting plasma generates magnetic fields. The energy that powers this dynamo ultimately comes from the nuclear fusion in the core, creating a connection between the sun's deepest interior and its most visible surface phenomena. The study of the sun's energy production has also provided crucial insights into stellar evolution throughout the universe. By understanding how our sun generates and transports energy, astronomers can better understand the life cycles of other stars and the conditions that might exist around them. This knowledge is essential for understanding the potential habitability of exoplanets and the likelihood of finding life elsewhere in the galaxy. The sun's energy production represents one of the most successful applications of nuclear physics to astronomy. The theoretical understanding of nuclear fusion developed in the early 20th century provided the key to understanding how stars shine, resolving a puzzle that had perplexed scientists for centuries. The discovery that stars are powered by nuclear fusion was one of the great triumphs of modern physics, demonstrating the power of scientific theory to explain phenomena on the grandest scales. The energy that streams from the sun every second represents the conversion of matter into energy on a scale that dwarfs any human technology. Yet this process occurs naturally in the hearts of stars throughout the universe, driven by the fundamental forces of nature and the simple fact that helium nuclei are more tightly bound than hydrogen nuclei. The sun's energy production is a testament to the elegance of the physical laws that govern our universe, creating the light and heat that make life possible through processes that operate at the most fundamental level of matter and energy. As you settle into the quiet of evening, perhaps you can appreciate the remarkable journey that the light around you has taken. Every photon that illuminates your world began its existence in the nuclear furnace of the sun's core, created in the violent collision of hydrogen nuclei under conditions of unimaginable temperature and pressure. That light traveled for thousands of years through the sun's interior, was transformed and retransformed countless times, and then raced across 93 million miles of space to reach your eyes. The sun's energy production is a story of transformation and patience, of violence and beauty, of the smallest particles and the largest structures. It's a process that has been ongoing for 4.6 billion years and will continue for billions more, providing the steady energy source that powers the magnificent complexity of life on Earth. In the gentle warmth of sunlight, in the growth of plants, in the circulation of our atmosphere and oceans, we see the ongoing influence of nuclear processes that occur in a realm of temperature and pressure so extreme that they challenge our imagination. The sun's energy production connects us to the fundamental forces that shape the universe, reminding us that we live in a cosmos where matter and energy dance together in patterns of incredible beauty and complexity. The light that guides our days and the warmth that sustains our lives are products of the same nuclear processes that occur in stars throughout the galaxy, making us part of a vast cosmic community bound together by the common physics of stellar energy production. Tomorrow, when the sun rises again, it will bring with it not just another day of light and warmth, but the ongoing testament to the power of nuclear fusion to transform matter into energy, darkness into light, and the simple into the sublime. The sun's energy production is one of the most remarkable processes in the universe, yet it occurs with such quiet consistency that we often take it for granted. In that consistency lies perhaps the greatest miracle of all, the steady, reliable energy source that has made possible the incredible journey from simple atoms to complex life, from darkness to consciousness, from the nuclear fires of stellar cores to the gentle warmth of a summer day. The sun's energy production is also a reminder of the interconnectedness of all things in the universe. The carbon in your body was forged in the heart of an ancient star. The oxygen you breathe was created in stellar cores and scattered into space by supernova. And the energy that powers your metabolism comes directly from the nuclear fusion occurring in the sun's core right now. We are not separate from the cosmic processes that surround us. We are part of them, temporary arrangements of matter and energy that have learned to contemplate their own origins. In this vast cosmic story of energy production and transformation, we find both humility and wonder. Humility in recognizing our small place in the grand scheme of stellar evolution, and wonder in discovering that we are made of the same materials and powered by the same processes that light the stars. The sun's energy production is not just a distant astronomical phenomenon. It's the source of every breath we take, every thought we think, and every moment of consciousness we experience. As we drift towards sleep, carried by the gentle rhythm of our breathing and the steady beating of our hearts, we can rest in the knowledge that the sun's nuclear furnace continues its ancient work, converting hydrogen into helium and matter into energy with the same patient consistency that has characterized its operation for billions of years. The sun's energy production is the heartbeat of our solar system, the rhythm that underlies all life on Earth, and the source of the light that will greet us when we wake to another day in this remarkable universe we call home. The sun's relationship with time operates on scales that challenge our human perception of permanence and change. While we experience the sun as a constant, reliable presence in our daily lives, our star exists in a state of continuous evolution, changing slowly but inexorably over timescales that span geological ages. Consider the sun's rotation, which reveals itself through the gradual movement of sunspots across the solar disk. Unlike Earth, which spins as a solid body, the sun rotates differentially. Its equator completes a rotation in about 25 days, while regions near the poles take 35 days to make the same journey. This differential rotation is like a cosmic clock, with different hands moving at different speeds, creating the shear forces that twist and tangle the sun's magnetic field lines. This rotation rate hasn't always been the same. When the Sun first formed from the collapse of a molecular cloud, it spun much faster, perhaps completing a rotation in just a few days. But as the young Sun developed its magnetic field and began generating a solar wind, it gradually slowed down through a process called magnetic braking. The solar wind, carrying away angular momentum as it flows into space, acted like a cosmic brake, slowly reducing the Sun's rotation rate over millions of years. The Sun's luminosity, its total energy output, has been gradually increasing throughout its lifetime. This slow brightening occurs because as the Sun converts hydrogen into helium in its core, the average molecular weight of the core material increases. This makes the core slightly more compressed, which increases the temperature and pressure, which in turn increases the rate of nuclear fusion. The result is a gradual but steady increase in the Sun's energy output. This phenomenon, known as stellar evolution, means that the Sun today is about 30% brighter than it was when it first began nuclear fusion 4.6 billion years ago. This gradual brightening will continue throughout the Sun's main sequence lifetime, with the luminosity increasing by about 1% every 100 million years. While this might seem like a small change, it has profound implications for the long-term habitability of Earth. The early Earth, receiving 30% less solar energy than today, should have been frozen solid according to simple climate models. Yet geological evidence clearly shows that liquid water existed on our planet's surface, even in its earliest epochs. This apparent contradiction, known as the faint young sun paradox, suggests that Earth's early atmosphere must have been very different from today's, probably containing much higher concentrations of greenhouse gases that trapped enough heat to keep the planet warm despite the weaker sun. As the Sun has gradually brightened over geological time, Earth's atmosphere has evolved to maintain relatively stable temperatures. This delicate balance between solar evolution and atmospheric chemistry has been crucial for the development and persistence of life on our planet. It's a reminder that the conditions we consider normal and stable are actually the result of a complex interplay between stellar and planetary evolution unfolding over billions of years. The Sun's magnetic field also evolves on multiple timescales. The familiar 11-year sunspot cycle represents just one rhythm in a complex symphony of magnetic variations. Longer-term changes in solar magnetic activity occurring over centuries or millennia can affect Earth's climate in subtle but measurable ways. The Maunder minimum, a period from roughly 1645 to 1715, when very few sunspots were observed, coincided with particularly cold temperatures in Europe and North America during what's sometimes called the Little Ice Age. These long-term variations in solar activity are thought to be related to changes in the Sun's internal dynamo, the process that generates its magnetic field. Just as the Sun's rotation has evolved over time, so too has the strength and pattern of its magnetic field generation. During the Sun's youth, when it rotated much faster, its magnetic activity was likely much more intense, producing flares and coronal mass ejections far more powerful than anything we observe today. The Sun's chemical composition is also slowly evolving. The nuclear fusion in the core not only converts hydrogen into helium, but also creates trace amounts of heavier elements through secondary reactions. Over billions of years, these processes have slightly enriched the Sun's core in helium and heavier elements while depleting it of hydrogen. This gradual change in composition affects the Sun's internal structure and will eventually lead to dramatic changes in its behavior. The helium produced by nuclear fusion accumulates in the Sun's core because it's heavier than hydrogen and doesn't participate in the fusion reactions that power the Sun. Over time, this helium ash builds up, creating an inert core surrounded by a shell of actively fusing hydrogen. This accumulation of helium will eventually affect the Sun's energy production and internal structure, leading to the next phase of stellar evolution. The Sun's future evolution is written in the physics of stellar structure and nuclear fusion. In about 5 billion years, The hydrogen in the Sun's core will become so depleted that fusion reactions will no longer be able to generate enough energy to support the Sun's outer layers against gravitational collapse. When this happens, the Sun will begin a dramatic transformation that will fundamentally change its character. The core will contract and heat up, while the outer layers will expand and cool, transforming the Sun into a red giant star. During this phase, the Sun will grow to perhaps 100 times its current size, possibly engulfing the inner planets. The surface will become cooler and redder, but the total energy output will actually increase as the Sun's surface area expands dramatically. This red giant phase will last for about 1 billion years, during which the Sun will experience dramatic changes in its structure and behavior. The expanded outer layers will become unstable, pulsating, and ejecting material into space. The Sun's magnetic field will weaken and become more chaotic as the outer layers expand and cool. Eventually, the Sun will shed its outer layers entirely, creating a beautiful planetary nebula, a glowing shell of gas expanding into space. What remains after this mass loss will be a white dwarf star, a hot, dense remnant about the size of Earth, but containing about half the mass of the current Sun. This white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark cinder drifting through space. The nuclear fires that have burned for billions of years will finally be extinguished, and the Sun's long journey from birth to death will be complete. But these dramatic changes are still far in the future. The Sun is currently in what astronomers call the main sequence phase of stellar evolution, the long, stable period when a star fuses hydrogen into helium in its core. This phase accounts for about 90% of a star's lifetime, and the Sun is roughly halfway through this stable period. We exist during the Sun's golden age, when it burns steadily and reliably, providing the consistent energy source that complex life requires. The Sun's evolution is part of a larger cosmic story of stellar birth, life, and death that has been playing out throughout the universe for billions of years. The Sun is what astronomers call a third-generation star, formed from material that was enriched by the nuclear processes in earlier generations of stars. The heavy elements in the Sun, and in the planets and life forms that orbit it, were created in the nuclear furnaces of ancient stars and scattered into space when those stars died. This cosmic recycling process means that the Sun's evolution is connected to the evolution of the galaxy itself. The Milky Way has been gradually enriched in heavy elements over its 13 billion year history, as successive generations of stars have processed hydrogen and helium into the full periodic table of elements. Each generation of stars has been slightly more metal-rich than the last, creating the conditions necessary for the formation of rocky planets and the complex chemistry of life. The Sun's position in the galaxy has also evolved over time. Our solar system orbits the galactic center every 225 million years, but this orbit isn't perfectly circular. The Sun's galactic orbit carries it up and down relative to the galactic plane, periodically exposing our solar system to different radiation environments and potentially affecting the rate of cosmic ray bombardment of Earth. These galactic influences operate on timescales much longer than human civilization, but they may have played a role in shaping the long-term evolution of life on Earth. Some scientists have proposed that the Sun's passage through spiral arms, or its oscillations above and below the galactic plane, might be correlated with mass extinction events in Earth's history, though this remains a topic of active research and debate. The Sun's evolution is also influenced by its interaction with the interstellar medium, the thin gas and dust that fills the space between stars. As the Sun moves through the galaxy, it encounters regions of different density and composition, which can affect the size and shape of the heliosphere and potentially influence the cosmic ray environment in our solar system. Currently, the Sun is moving through a region of space called the local interstellar cloud, a relatively warm and low-density region that extends for several light-years around our solar system. But in about 10,000 years, the Sun will enter a different region called the local bubble, which may have different properties that could affect the boundary between the solar wind and the interstellar medium. The study of the Sun's evolution provides crucial insights into the life cycles of stars throughout the universe. By understanding how our Sun has changed over time and how it will continue to evolve, astronomers can better understand the behavior of other stars and the conditions that might exist around them. This knowledge is essential for understanding the potential habitability of exoplanets and the likelihood of finding life elsewhere in the galaxy. The Sun's evolution also helps us understand the broader processes of cosmic evolution. The gradual enrichment of the universe in heavy elements, the formation of planetary systems, and the development of conditions suitable for life are all part of a grand cosmic story that began with the first stars and continues today. The Sun's journey from birth to death is just one chapter in this larger narrative of cosmic evolution. Recent observations of other stars at different stages of evolution have provided valuable insights into the Sun's past and future. Young stars, similar to the Sun but much more active, help us understand what our Sun was like in its youth. Older stars, approaching the end of their main sequence lifetimes, give us glimpses of the Sun's future. White dwarf stars show us what remains after stars like the Sun have exhausted their nuclear fuel and shed their outer layers. The Sun's evolution is also closely linked to the evolution of the planets in our solar system. As the Sun gradually brightens over time, it will eventually make Earth too hot for liquid water to exist on its surface. But this same increase in solar luminosity might make Mars more habitable, as its thin atmosphere and greater distance from the Sun could provide more Earth-like conditions in the distant future. The moons of the outer planets, particularly those of Jupiter and Saturn, might also become more hospitable as the Sun evolves. The subsurface oceans of Europa, Enceladus, and other icy moons are currently maintained by tidal heating from their parent planets. As the Sun brightens, these worlds might develop more temperate surface conditions, potentially expanding the habitable zone of our solar system. The Sun's evolution reminds us that change is the only constant in the universe. The conditions we consider normal and stable are actually temporary states in a continuous process of cosmic evolution. The Sun that lights our days and warms our world is not the same Sun that shone on the first life forms billions of years ago, nor will it be the same Sun that future generations might observe billions of years from now. Yet for all its gradual changes, the Sun has maintained the remarkably stable conditions that have allowed life to flourish on Earth. The slow pace of stellar evolution, measured in millions and billions of years, has provided the long-term stability that biological evolution requires. The Sun's patient, steady energy output has been the foundation upon which the entire drama of life on Earth has unfolded. As we rest in the gentle embrace of evening, we can appreciate that we are witnessing just one moment in the Sun's long evolutionary journey. The light that fades from our sky at sunset carries with it the same nuclear energy that has powered our star for billions of years, but it emerges from a Sun that is subtly different from the one that rose this morning, changed by the countless fusion reactions that have occurred in its core throughout the day. The Sun's evolution is a reminder of the deep timescales on which cosmic processes operate. While human civilization has risen and flourished in just a few thousand years, the Sun has been patiently burning for billions of years, providing the steady energy source that has made our brief moment of consciousness possible. In the grand scheme of stellar evolution, human history is just a fleeting instant, yet it's an instant filled with unprecedented meaning and significance. The Sun's journey through time connects us to the broader story of cosmic evolution, reminding us that we are part of a universe in constant motion and change. The elements in our bodies were forged in the hearts of earlier generations of stars. The energy that powers our lives comes from nuclear processes in the Sun's core, and our future is intimately connected to the slow evolution of our star. In this cosmic perspective, we find both humility and wonder. Humility in recognizing our small place in the vast scheme of stellar evolution, and wonder in discovering that we are conscious participants in a story that began with the first stars and will continue long after our sun has faded. The sun's evolution is not just an astronomical phenomenon. It's the backdrop against which the entire drama of life and consciousness has played out. As you drift towards sleep tonight, perhaps you can sense something of the sun's patient journey through time. Though it appears unchanged from day to day, our star is slowly evolving, gradually brightening, subtly changing its character as it converts hydrogen into helium in its core. The sun's evolution is a testament to the power of time and the fundamental forces of nature to create change on scales that dwarf human experience. Tomorrow, when the sun rises again, it will be imperceptibly different from today, slightly brighter, slightly more evolved, carrying a bit more helium in its core and a bit less hydrogen. This gradual change, invisible to our senses but inevitable according to the laws of physics, reminds us that we live in a dynamic universe where even the most stable and permanent-seeming features are actually in constant flux. The sun's evolution is also a reminder of the preciousness of our current moment in cosmic history. We exist during a brief window when the sun burns steadily and reliably, when Earth's climate is stable and hospitable, when the conditions for complex life and consciousness are perfectly aligned. This moment will not last forever, but it has lasted long enough for the universe to become aware of itself through us. In the sun's slow dance through time, we find a rhythm that connects us to the deepest patterns of cosmic evolution. The nuclear processes that power our star operate according to the same physical laws that govern the behavior of matter and energy throughout the universe. The sun's evolution is part of a vast cosmic symphony that has been playing since the first stars lit up the darkness, and it will continue long after our brief moment of consciousness has passed. The sun's journey through time is ultimately our journey too. We are children of stellar evolution, temporary arrangements of matter and energy that have learned to contemplate their own origins. The sun's evolution has shaped the conditions that made our existence possible, and its future evolution will determine the ultimate fate of our world. In studying the sun's passage through time, we are really studying our own place in the grand narrative of cosmic evolution. As we settle into the quiet of night, we can rest in the knowledge that the sun's evolution continues its ancient rhythm, slowly and patiently transforming our star according to the immutable laws of physics. The sun's journey through time is a reminder that we are part of something much larger than ourselves. A cosmic story that began billions of years ago and will continue for billions more. A story in which we play a small but meaningful role. The sun's evolution connects us to the fundamental processes that shape the universe, reminding us that we live in a cosmos where everything is connected, where the past influences the present, and where the future is written in the language of nuclear physics and stellar mechanics. In the sun's patient journey through time, we find both the humility to recognize our place in the cosmic order and the wonder to appreciate the magnificent complexity of the universe we inhabit. The sun's future beckons us to consider timescales that stretch far beyond human comprehension. Yet these distant chapters of our star's story illuminate the profound nature of cosmic change. In approximately 1 billion years, the sun's gradually increasing luminosity will trigger a runaway greenhouse effect on Earth. Our oceans will begin to boil away, and the water vapor in our atmosphere will escape to space, leaving behind a world as barren and lifeless as Venus is today. This transformation won't happen overnight. It will unfold over millions of years, giving life on Earth ample time to adapt or perhaps even migrate to more hospitable worlds. By then, humanity, if we still exist, will have had 1 billion years to develop technologies we can barely imagine, to explore distant star systems, and to ensure that the spark of consciousness we represent continues to burn somewhere in the galaxy. But the sun's story doesn't end with Earth's transformation. Our star will continue its steady fusion of hydrogen into helium for another 4 billion years after that, maintaining the same reliable energy output that has characterized its middle age. During this vast span of time, the outer planets may become more hospitable. Mars might develop a thicker atmosphere as the increased solar radiation warms its surface. The icy moons of Jupiter and Saturn could see their subsurface oceans expand and perhaps even break through to the surface, creating new worlds where life might flourish. When the Sun finally exhausts the hydrogen in its core, the transformation will be both dramatic and beautiful. The core will contract and heat up, while the outer layers expand and cool, creating a red giant star that dwarfs our current Sun. During this phase, the Sun will pulsate gently, breathing like a cosmic organism as it adjusts to its new internal structure. The surface will glow with a cooler, redder light, but the total energy output will increase as the Sun's surface area expands. This red giant phase will last for about 1 billion years, during which the Sun will gradually shed its outer layers in a series of gentle exhalations. These layers will form expanding shells of gas that will glow with the light of the hot white dwarf core that remains. The result will be a planetary nebula, one of the most beautiful objects in the universe, a gossamer sculpture of light and gas that will persist for thousands of years before fading into the cosmic background. The white dwarf that remains will be incredibly dense, packing about half the mass of the current Sun into a sphere roughly the size of Earth. This stellar remnant will be initially very hot, glowing with a brilliant white light that will slowly fade over trillions of years. The nuclear fires that have burned for billions of years will finally be extinguished, and the Sun will begin its long journey toward becoming a cold, dark cinder drifting through space. Yet even in death, the Sun will continue to give. The heavy elements forged in its core over billions of years will be scattered into space during the planetary nebula phase, enriching the interstellar medium with the raw materials for future generations of stars and planets. The carbon, oxygen, and nitrogen that once flowed through living organisms on Earth will drift through space until they are incorporated into new worlds, perhaps seeding new forms of life in distant star systems. This cosmic recycling process has been ongoing throughout the universe's history. The Sun itself is made partly from the ashes of earlier stars, and the elements that make up our bodies were forged in stellar cores that died billions of years ago. We are part of an ancient cycle of stellar birth, life, and death that connects us to every corner of the cosmos. The Sun's ultimate fate reminds us that nothing in the universe is permanent, yet everything is connected. The energy that powers our lives today will outlive us by billions of years, continuing to fuel the nuclear reactions in the Sun's core long after human civilization has been forgotten. The light that illuminates our world will continue to shine across the cosmos, carrying with it the legacy of our star's long and magnificent life. As we contemplate these vast timescales, we might feel a sense of cosmic loneliness, recognizing how brief our moment in the Sun's story truly is. But there's also profound beauty in this perspective. We exist at a perfect moment in cosmic history, when the Sun burns steadily and reliably, when Earth's climate is stable and hospitable, when the conditions for consciousness and wonder are perfectly aligned. The Sun has been our faithful companion for all of human history, rising each morning with clockwork precision, marking the passage of days and seasons, providing the energy that powers every aspect of our existence. It will continue to be our companion for billions of years to come, long enough for countless generations to experience the joy of sunrise and the peace of sunset, to feel the warmth of sunlight on their faces, and to marvel at the beauty of our cosmic home. In the end, the Sun's story is also our story. We are children of stellar evolution, temporary arrangements of matter and energy that have learned to contemplate their own origins. The Sun's light flows through our veins, powers our thoughts and connects us to the vast web of relationships that bind all things in the universe together. Tonight, as you rest in the gentle embrace of darkness, remember that you are part of this magnificent cosmic story. The sun's light that faded from your sky this evening will return tomorrow, carrying with it the same nuclear energy that has powered our star for billions of years. In that light, you will find not just illumination for another day, but a connection to the deepest processes that govern the universe itself. The sun's story is far from over. It will continue to burn for billions of years, providing light and warmth to whatever forms of life evolve to replace us. Its future evolution will create new worlds and new possibilities, ensuring that the universe remains a place of wonder and discovery for eons to come. In the sun's patient journey through time, we find both the humility to recognize our place in the cosmic order and the inspiration to make our brief moment of consciousness meaningful. So rest well, fellow travelers, in this cosmic dance. The sun's story continues, and we are privileged to be part of it, to witness its glory, and to carry forward the light of consciousness that its energy has made possible. Tomorrow will bring another day in the sun's long story, another opportunity to marvel at the star that makes everything possible, another chance to feel connected to the vast and beautiful universe we call home. The sun's light will guide us through whatever challenges lie ahead, just as it has guided life on Earth for billions of years. In its steady, reliable energy, we find not just the power to illuminate our world, but the inspiration to reach for the stars, to explore the cosmos, and to ensure that the spark of wonder and curiosity that defines us continues to burn brightly in the magnificent theatre of space and time. And just like that, we've circled the story of our sun, from its blazing core to its gentle rays that touch your face each morning. It's always been there, watching over our tiny world, fueling life, guiding time, and silently reminding us how small we really are in the grand design of space. If your eyes are already closed, rest well. And if you're still with me, thank you for joining this quiet journey. I'll see you again. Good night. Take care. Cheers.